At the end of yesterday, I had this idea called slope fields. And the idea behind the slope field was a collection, a generation of all the different slopes at different points on the plane. And the purpose is that sometimes we have differential equations that dy dx equals something that we cannot easily solve. One such example put up there yesterday is that x plus y. Why can't we solve that? Let's solve it. I had to go through and I looked up a strategy to getting through that. Can we solve when we've got this dy dx equals x plus y? Now, what we tried yesterday was we separated, and this is going to be a term, we have separable variables. We cannot separate that x and y. If we cross multiply, we would have dy equals x dx, which we can integrate, plus y dy. If we tried to integrate y dx, thank you, y dx, well, we'd have the integral of dy, which we can do. We'd get y. I'm going to switch to my Sharpie. Here's x.
The video isn't going to be the same because we want to see you pull it out of your pocket.
That's correct. That's an x, and so. Did I do like the videos last year in pre-calc at all? Maybe, I think a couple of them I just had were old ones. Now, if we're going to integrate x dx plus y dx, dealing with that, it becomes a little bit messy, specifically because that x plus y dx, that y, because our function is y equals, and so it's in terms of itself. How do we do that? This one, I actually had to look up how to work through it. I'm going to rewrite this as y prime equals x plus y. Y prime is the same thing as dy dx. Here's how we would go through this. We're going to multiply that entire equation by e to the negative x. Why? Because it's going to work. That's going to give us e to the negative x y prime equals e to the negative x times x plus y times e to the negative x. Rearranging things, that's going to give us e to the negative x y prime minus y e to the negative x equals e to the negative x times x. If we integrate that whole side, we're going to integrate that whole side. This and that's with respect to x. Well, this is actually something called integration by parts. This turns into e to the negative x multiplied by y. And think about it, if we took the derivative of e to the negative x times y, we'd have to use the product rule. The product rule would turn into that. On the right side, that's going to give us negative e to the x times x minus e to the negative x plus c. Integration by parts. You'll see it next year. Rearranging some things, I'm going to divide both sides by e to the negative x. That's going to give us y equals, all right, negative e to the negative x divided by e to the negative x is going to give us negative x. C divided by that is going to get us c e to the x. That divided by itself gets us, there's a minus x in there, there's a minus 1 in there. There is the general solution to that system, to that differential equation. Oh boy. Now, instead of doing that, we can use a slope field to represent. And so let's actually go through. What does this look like? Well, it depends on the C. The slope field idea was a way of looking at slopes at particular points. So I want to, on our paper, I want to graph dy dx equals x plus y, the differential equation of x plus y. It gives us the slope at specific points. Now I'm going to break it apart that every 2 boxes is worth 1, so we're not overcrowding. Every 2 boxes is worth 1. We can take coordinates on our grid And we can figure out what the slope would be at that point. At 0, 0, well, the coordinate x is 0, y is 0. The slope would be 0 plus 0. The slope is going to be 0. Any point across the horizontal axis, well, y is going to be 0. But if x is 1, then our slope would be 1. So I'm going to use a little line segment to indicate my slope is 1. Or on the left side, my slope would be -1. So if our curve passes through there, it's going to follow that curve. That's straight, that's not completely. The next, if x is 2 and y is, well, then x is going to be 2. I look up and try to find some boxes to get an idea of what a slope of 2 would look like. So I try to map out, I'm going to have a slope of 2. So it's going to be steeper when x is 2 and y is 0. X is 3, 3, 0. We're going to have a different slope. So I can figure out 1, 2, 3. It's going to be steeper still. -2, -3. So I use a little line segment to represent that going through those points, that would be what our curve looks like. The idea of differentiability is that our curve is locally linear. If we zoom in on a small part, it looks like a straight line. And so essentially the slope field tries to give us an idea of what things look like close by to where we're at. Now, one thing I think about, let's find all the spots where our slope is going to be 0. I can think about, okay, x plus y equals 0. That's going to be along the equation, the line y equals -x. Because if we've got x plus y equals 0, y is -x. Anywhere along that line, y equals -x, our slope is going to be 0. Let me see, 0, 0, 0, 0. If our curve is passing through that, we have all these sections where our curve is going to be 0. Did I mess that up? Nope. Here we go. We can figure out where on our curve our graph is going to be equal to 1. If I say like x plus y equals 1, it'll be y equals 1 minus x. So everywhere on the line, y equals 1 minus x, our slope is going to be 1. Well, 1 minus x, we have a y-intercept of 1, a slope is -1. So all these points, we're going to have a slope of 1. And I can put in these line segments to show that I have a slope of 1 along this area. I can do when is our slope equal to -1. X plus y would be -1. Y equals -1 minus x. Hopefully you see that there's this pattern that on these diagonals, we have these same slopes. The point here is that we're building up like an image of what our curve is going to be looking like by small little segments along the way. We're going to be 2 in there.
8 minutes, 50 seconds.
Yep, it happens. That's not the longest. And we can, the longest video ever?
Probably.
Lord of the Rings extended version or something?
No, it's not that.
I don't know. Full, watching all the Star Wars movies back to back. We can keep on putting in our values. There's the 1/3, the 3, slope of 3 would be even steeper along that diagonal, and so forth. 3. And I think I got off there. I lost a line. That's where I should be, and that's where I should be. We see that all of these segments start to give us a picture of what our curve might look like. This is where yesterday.
It says about it's 571 hours.
What is? The longest video is 570. Oh boy. Yesterday on the calculator, I gave you a program. Yeah. I'm just gonna edit out the video. Come on and focus. Yesterday I gave some of us a calculator program. We had to figure out if we had the Keller edition. I could not get it to you. We had that program, slope field, and we'll fix that in a little bit. For those of us that don't have it, did not get it. Put the code up. The way the slope field program works, in y equals, we're going to put the equation that we have. So if we want the slope field for dy dx equals x plus y, I put that in. Now I'm on my standard Windows Zoom 6. We cannot graph x plus y. It's going to take y as being a constant. This program slope field, if we have our differential equation in, I can go into slope field. I'm going to run it. It goes through and plots our intervals, giving us the idea of all of these locally linear segments. So we can see in there that, okay, that's where all the slopes were equal to 0. It's actually not showing it too well. Based upon the window that we have. By my graph paper, I was going from -5 to 5. So we can change the window to get more detail. And the slope field shows at this interval, we locally linear, it looks like this. And so it gives us a general trend of what the graph could be, what the graph might be looking at. This is the idea of a slope field. So at each coordinate, especially if we are in terms of x and y, we can figure out the slope there. This helps us because sometimes we cannot actually find a particular solution to the system of equations. This helps gives us an idea so that if we were finding some point, oh, okay, right there, it looks like that, but then it's going to connect over, but then it's going to be steeper, but then it's going to be steeper, and then it's going to go up. Here it's less steep, less steep. So we might have some equation that passes through a given point that looks like that. Or if we pass through this point, here we're going down, but then we're going more down, and then we go up, and then it's less steep. We might have a particular solution that looks like that. And so the slope field gives us an idea of how a particular region might look. That's the idea behind the slope field. How's that look right now? Is that okay? Make sense?
Do it again.
Let's do it again.